Hello, everybody. I hope you all are having a great day and welcome to the third day of the Qubit Hub IBM Qiskit File Fest 2025. And today we're happy because we are having five exposers, and one of them is Ricardo Rivera. Hello, Ricardo. How are you?
Hey, good, thank you.
Perfect. So, if you agree, I'll read your abstract, your bios, and then we can begin with your talk.
Yes.
Okay, so Ricardo is a PhD candidate at the Institute of Physics of the Slovak Academy of Science and the Research Center for Quantum Information. His work is in Hamiltonian complexity, a field mixing both theory and practice, which sits at the interaction of the quantum physics, mathematics, and computer science. His everyday work is mostly on the theory side, but he has worked as a quantum software intern at Spacecraft and Algorithmic, two prominent quantum computing startup companies, where he has applied this knowledge and developed quantum computing algorithms for real use cases. And today, with Ricardo, we're having his talk with the title Which Problems Can and Can't Quantum Computers Solve? Giving a definite answer to this question could either be the cause for celebration or concern, as quantum computing now connects many of the natural sciences and received significant attention and funding across the globe. The study, this, to study this question formally, we must turn to a subfield of computer science called complexity theory. Here, we will introduce some of the basics of this field and illustrate the best answer we can provide currently. Along the way, we will discuss the relationship between classical and quantum computers and whether one is truly more powerful than the other. Finally, we will discuss some shortcomings of the picture we painted so far, which relate to approximation algorithms, average case complexity, and quantum computers without fault tolerance. So, Ricardo, very happy to have you here today.
Thank you very much. I'm happy to be here as well. So today I wanted to tell you a little bit about what I do in my work and why I find this like super exciting. So, uh, as I was just introduced, so I will be talking about which problems can and can't a quantum computer solve. And I think that this question is very important currently because there's a lot of hype around quantum computing, and uh, people claim that quantum computers can do everything, and it's not true. And a lot of people, like the media, are putting their money into quantum computing companies and stuff when they are not kind of like really informed. Like quantum computers are good for some things, but they are not what everyone makes them out to see. So I will try to answer this question with the best knowledge that we have so far. So my goal for you is to see some examples of the types of problems that we can solve with a quantum computer, with a classical computer, and problems that we can or can't solve with a and can't solve as well. Second goal will be to understand this diagram that I have here. And finally, to convince hopefully some of you that this is indeed very cool and that it's worth studying. So maybe, I don't know, for your master's, your PhD, you might want to do this, which I recommend. Okay. So first, I wanted to tell you a little bit about me. So I am Mexican, but I haven't been in Mexico for a while. So I've went for my undergrad to the University of British Columbia in Canada, where I did physics and mathematics. Then for my master's in Amsterdam, where I did theoretical physics. And now I'm currently in my last year of the PhD in the Slovak Academy of Sciences, doing something called Hamiltonian complexity theory. And this field is the intersection of many other fields that you may be familiar with. So we have math, over here. See? So we have math, we have computer science, and quantum physics. And before starting on this PhD, I only knew math and quantum physics. So I really, at the beginning of it, I really had to learn a lot about computer science in order to do what I do now. But I'm telling you this to encourage you to, I think, pursue what you really want. And then it doesn't matter if you're good at it. It doesn't matter later if you decide to switch to something, or like try to learn something new and try to get into a new area that you may not be experienced. So besides that, I've also met a lot of colleagues that were in a similar situation. They studied engineering, they studied some of them even biology, and now they're doing quantum. So what I think, and a message that I want to get across, is that there's no wrong choice. You can always go into study quantum later. Right. So besides this, I've also done a couple of internships at some quantum computing startups. So Facecraft in the UK, and now I think they have some offices in the US as well. And most recently in Algorithmic in Finland. And I will tell you a little bit more about what I did in these companies later on in the talk. So feel free to ask me any questions that you might have about these as well. So, all right. So let's jump in. So the outline for the talk is the following. So first, we're going to formalize the question, because the way that I have phrased it at the moment is very tricky. So we're going to have to actually formalize that a little bit more. Then I'm going to answer this question for classical computation, and then quantum computation. And then finally, we're going to go over some objections that you may have with this picture or how I'm answering this question. Right. So let's begin. So which problems can and can't a quantum computer solve? And I think first, the obvious thing is that we should be talking about computational problems, right? We don't care whether a quantum computer can clean your room, wash the dishes. That's not what we are here for. We care about computational problems. All right. And second is that this question, the way that it's phrased here, is actually quite trivial. And that is that quantum computers and even classical computers can solve almost every problem we know of if they have enough resources to do so. So, and here by resources, we mean like time or memory, which in computers just means RAM, the number of queries, energy, or whatever you want. So even classical computers can do everything that quantum computers can do if you give them enough time or memory, which is interesting. So the way that this question is formed here, it's not good, right? Because we don't care if the problem can be solved in 3,000 years from now. Well, we want answers within a reasonable amount of time. So that is just what I just mentioned. So the right answer, the right question to study is whether which problems can and can't a quantum computer solve efficiently. That is an important question. So now, how do we define what efficient is? And for this, I have a little example here. So suppose that your phone was stolen and the thieves don't know anything about it. And your phone, it has like 4 or 5 or 6 digit pin. I think it depends on which kind of phone you have. But let's suppose that you have an n-digit pin. So the best thing that the thieves can try to do is literally just try all combinations. If they don't know anything about you, if they don't know your birthday or something, which are common passwords, then the best they can do is just try one by one, right? So if we have a 4-digit PIN, there are 10 to the 4 combinations they could try. And if we suppose that it takes the thieves 1 second to input one combination, then it'll take them 15 minutes to break, to unlock your phone. And now if you have a 6-digit PIN, then there's 10 to the 6 combinations, and approximately it might take them 1 day, right? And then if you have 8, then it might take them 3 years. So just because they can do it, it doesn't mean that it's efficient. And this algorithm is not, I wouldn't say that it's efficient, right? So we will define inefficient as an algorithm that scales exponentially in time. And where here exponentially, it is represented by this equation or formula, I guess, where this just means of order c to the n, where c is a constant. And this is the same form that you can see here, right? So the constant here is 10, and n is just the number of digits that are in your PIN. So this algorithm is inefficient by this formula, I guess you can see. So now, what is efficient? So efficient is an algorithm that scales polynomially in time. I've also decided to focus on time. So in this talk, we're only going to be talking about time. At the moment, I don't really care about memory, queries, or energy, but it's also valid questions to ask as well. But complexity theory mostly focuses on time and memory. But today, I'll only be talking about time. All right. So there is another thing that we have to consider, and that is that problems have different forms of expressing themselves, and we call these instances. So take, for example, Sudoku, which I don't know if you young people know what these are. But here you have this grid of numbers, and the job or your task is to fill in this grid such that the numbers 1 to 9 appear exactly once in each column, every row, and also in every little square here. And there is different difficulties for this problem. So you have a beginner one, which are the ones that have usually a lot of numbers. But you also have intermediate and expert. And usually the difficulty depends on the numbers that you already have filled in, which are kind of like the hints that you have available for you. But also, you can define Sudokus on smaller or larger grids than the 9x9 that we have over here. So these are what we call instances of the Sudoku problem. And now, how does this relate to what I was talking before? And it is that efficient algorithms must be efficient for all instances. So even the most difficult ones. That is what we do in complexity theory. Okay, so now we have the full question here. And then we say that we can solve a problem if there is an efficient algorithm that solves all instances of the problem, including the hardest case ones. And we say that we can't solve a problem if there is no efficient algorithm that solves all instances of the problem. And here, remember that efficient means polynomial scaling as a function of the problem size. And I will be quiet for 20 seconds or so because I really want to get you to process this question and what everything means. And by now, you should probably have some objections. So if you have some objections already, please feel free to type them in the chat. And okay, I will be quiet for 20 seconds so you give you enough time to process this question. I don't see objections in the chat just yet, but if you've understood the question so far, you may have at least one, which is this one. So what if the worst case instances do not occur very often? So we are making this statement for all instances, even the hardest ones. But in reality, I don't know. It's still kind of like an open question whether you get the hardest instances all the time, or maybe those ones rarely appear. So in the end, we'll come back and kind of like explore this a little bit more. But for now, let's just continue with that statement. This. Okay. So, like I mentioned, this is all from a sub-branch of computer science called complexity theory, where we study the resources that an algorithm needs to solve the problem. And we want to focus on the worst case because it really tells you something about the essence of the problem, about what makes a problem hard or what makes a problem easy. And also, complexity theory groups those problems with similar difficulty into something that we call complexity classes. And another thing that complexity theory does is that it allows us, so both of these things allows us to talk about problems as a whole and find relationships between some of these problems. So right now, it might not mean a lot to you, but I feel like by the end of the talk, you'll have a clearer idea about what I mean with these things. Okay, and to finally get into the meat of the talk, there is one more piece of theory that I should explain. And this is the notion of reductions, which is essentially that a problem can be transformed into another problem. And by doing that, I can solve the first problem or kind of like associate some difficulty with the first problem by translating it into another problem. Okay, but this will be clearer with some examples. So the first example is, for example, if I want to find the median in a list of numbers. So I can do this by sorting the list, right, which is a different problem, and then just take the middle element. And then this one I came up with recently, and it's very dumb, but I kind of like it, and it might give you some intuition about it as well. So suppose that I'm learning machine learning, and I have successfully made a classifier for squirrels. Like I give pictures of squirrels, and it tells me whether they are actually squirrels or whether they are something else. And it does so with very, very high probability, so it's almost correct. And now let's say that I wanted to make a classifier for dogs. But imagine that I don't have enough data for dogs, or I'm just too lazy. So instead, what I can do to classify dogs is that I can disguise my dogs as squirrels, right? Because then I will give those to my classifier, and it'll see a squirrel, and it'll tell me, oh, that is a squirrel. No, that is not a squirrel. And here we have this equality that squirrel means dog. So essentially, by disguising my second problem as the first, and I already know how to solve the first, I can solve the second problem. That is the general idea. Okay, hopefully that made sense, but if not, you can always ask questions. Okay, so now let's answer this question in the classical case, where classical means laptops and phones, your regular devices. Okay, so the complexity class that corresponds to problems that we can solve efficiently in a classical computer is P. And we can imagine these sets of problems via this little circle over here. So you can imagine that there's like some dots in there, and those correspond to problems that you can solve efficiently in your classical computer. So what are some examples that we have here? So for example, things that you kind of like do in your everyday life. So sorting a list of numbers is one example. So here, the problem is the following. So you're giving a list of numbers, and you have to sort it in ascending order. So if I give you these lists, there is a very simple algorithm that can do that. And I think many of you might already be familiar with it. So what I would do is I grab the first number that I have, and then I check whether it's less or equal to the following numbers. So I would go 2 is less than 7, yes. So I keep it. 2 is less than 5, yes. 2 is less than 3, yes. 2 is less than 1, no. So then I would grab this number, and then I would continue. But since I'm at the end, then I've already found that first, the smallest number. So after the first iteration, I already have this here, and that one will be fixed. So then we'll go for the second number. 2, is it less than 7? Yes. 2, is it less than 5? Yes, and so on. So in the second iteration, I will have already fixed the 2 because it's the smallest number there. And then in the third iteration, I will find the 3, and then in the fourth iteration, I will put the 5, and then voila, my list is ordered, right? So now let's analyze this algorithm in a little bit more detail. So what is the number of comparisons per iteration? This is approximately n, right? So in the first case, I compared 2 with 7, 2 with 5, 2 with 3, 2 with 1. So I pretty much went over the whole list. And in the first iteration, I did n minus 1. Remember that n is the size of the list, because I only had to check 4 numbers and so on. But these like n minus 1, n minus 2, for complexity theorists, it doesn't really matter. We'll just say that it's n. So I do this. I do n comparisons for each iteration. And there is about n or n minus 1 iterations, which gives us that the algorithm runs in O(n) squared time, or comparisons. So here I'm using time as it's not really the time that you measure in the clock, but the number of basic arithmetic operations or comparisons. So yeah. Then another example we have is matrix multiplication that you may all be familiar with. So here we have a 3 by 3 matrix and a 3 by 3 matrix, and I want to multiply these together, right? So how do I calculate this point, this entry that would go in the top leftmost part of this matrix here? So I'm sure that you're all familiar with it, but I would grab this first row and multiply it by this first column, right? We all learned this in middle school. So I would do something like this. 3 times 5 plus 3 times 5. Oh, that should be a 2 times 5 and 3 times 9, right? How many operations are there here? Well, turns out that there is 2n operations, right? So we have 3 multiplications and 3 summations. So yeah, Usually for an n by n matrix, then I would have 2n operations. And now I have to do this for all the other columns in that row, which would give me to a 2n squared operations. And then I also have to repeat this for every row of this matrix as well. So in total, I will have 2n cubed operations. And this notation that I have here, which is the big O notation, this just kind of gets rid of the 2 because it's not very important. So it is n cubed, and like I mentioned a couple of slides back, this is polynomial time. So this is an efficient algorithm for solving these two problems. And every year, more problems are added to this class. Why? Because we define new problems that we care about, or we come up with better algorithms, or we find ways to relate them to problems we already know in P, which is kind of like by the concept of reductions that I was talking about before. So if I have a problem that I don't know how to solve, and I can transform that into a problem that I know how to solve by disguising it, but not by adding a reasonable amount of things to it, then because I can solve the second problem in P efficiently, then I can also solve the first problem in P. So that's usually how these things go. And now a more exciting problem is something called the shortest path problem. Okay, so here in this problem, you are given a graph, which is this thing with vertices and lines. And you are asked to find the shortest path from one point to another. And here I took from the map of Mexico. And suppose that I want to go from Mexico City to Hermosillo. And these lines over here are the highways. And some highways, let's say, take a long time, take some amount of time, and I don't know, maybe this one over here takes quite a long time because there's some construction or something going on. Yeah, so we seek to answer this question. And at first glance, this question seems very, very hard, right? Because there are exponentially many paths and possibilities of getting there. So for example, I could go from here to here to here to here, there, and so on, right? It is not clear. And it was only like about 70 years ago that Dijkstra found an algorithm for this problem that is efficient. Unfortunately, I don't have enough time to really explain this algorithm, but if you're interested, go check it out in YouTube. There's very few, a couple of nice videos that explain that. So this example is very interesting and very non-trivial. All right. So now we go to the second part of the question. So what problems can't a classical computer solve efficiently? And the answer to this question is that everything we can prove that lies outside of P, where proof here is the more important part. And it turns out that proving that something is not in a complexity class is extremely, extremely difficult. We only know of very few problems, and they are not very natural. So what does this mean in our little diagram that we have? So let this square be all the problems that exist. And at the moment, this is P. And these ones are problems that we can prove that are not in P. Right? So what this means is that technically P could be gigantic. It just can't include those problems. So we don't know that. Okay, so this says that we do not know the answer to this question, essentially. But we have educated guesses on some of the problems that should be outside. And these are NP-complete problems. So now I will explain what I mean. What is NP here? What are complete problems? But At first, it might not make a lot of sense of what the connection is, but bear with me. Okay, so what is NP? So these are the types of problems where, given a solution, the answer can be verified efficiently with a classical computer. And a problem in this class is, for example, the Sudoku that we saw before. So if I give you the Sudoku, you can check whether it's correct or wrong just simply by going through all these rows, going through all the rows, going through all the rows, all the columns, and checking each one of those little squares that it's filled correctly. So to verify it, you should check one column, and to make sure that it's one that it has all of the 9 numbers, and the same for all the rows. And essentially, this algorithm, it can be done in n squared number of steps. So it is efficiently verifiable. And we have another problem that maybe you've heard about, which is integer factorization. So in this problem, you're giving a number, and you're asked to find what are its 2 prime factors. And I guess that you've already heard about it, because this is very famous in quantum computing. Because this problem can be solved with a quantum computer, and it is by Shor's algorithm. So maybe if you're learning about quantum computing in IBM or in some other platform, you've already come across this problem as well. Yeah. So suppose now that I give you x is equal to 837. And I give you the solution, which is 27 and 31. Then you can verify whether these are actually the 2 prime factors of x just by simply multiplying those together, right? So 27 times 31, and you'll very quickly see that this is actually 837. And the verification can be done in one step. So both of these 2 problems correspond to NP. And now this class has been even growing. Its importance has been growing in recently, right? Because it is very relevant given the rise of AI. So right now we are in a stage where we ask the AI for stuff, and we actually want to verify what the AI is saying is true or not. So here, for the integer factorization problem, I am the human, and I'm asking my AI, what are the 2 prime factors of 837? So then the AI would respond 27 and 31, and again, by multiplying those together, I can verify the answer, right? So figuring out which problems fall into this class is also very, very useful because of this reason. Like we can just ask anyone, the AI or someone, and then if they give us the solution, we can actually verify it. All right. So now, how does P, the class that we saw before, relate to this new complexity class? And it turns out that any problem in P is in NP. Okay. Why? Because the solution is not necessary in this case, because we can just compute the answer ourselves. And to illustrate this point, again, let us consider the shortest path. So now I ask the question, can I make it from Mexico City to Hermosillo in under 30 hours? And then if I give you this, show you this route, right? You can check. So this is 3, 6, 11, 18, 22, 24, 28. So yes, I can get there in under 30 hours. And verifying the answer here takes n time of order n. Because you can imagine if there's just a straight line and there's no loops or something like that, then you have to go through every node. So that explains why it's n. But like I mentioned, this is not necessary because I can just compute the answer myself using Dijkstra's algorithm. So that explains why every problem that is in P is also in NP. And if I have an efficient algorithm that solves a problem, like here, which is polynomial time, then that implies that this is efficient verification. Okay. And now here comes the important part. And this is that we think NP is bigger. Why? Because otherwise, every problem that can be verified efficiently can also be solved efficiently. So I tried this with my girlfriend. She was the guinea pig here. And so we don't think that this is possible, that this statement is possible. And this is one example. So I gave this Sudoku to my girlfriend, and it took her 40 minutes to solve. And she came up with this answer. And then she gave it to me, and then I verified it, and it took me about 2.5 minutes to verify. So it was very, very fast, right? But why do we think that this is not possible? So every problem that can, let's look at the statement again. So every problem that can be verified efficiently can be solved efficiently. This could also imply that I can prove theorems about mathematics or about whatever I want efficiently, because I can verify them efficiently. So if this is true, I would be able to solve, to prove theorems efficiently. We don't think this is possible. And the reason why it's so outrageous to think that Sudoku could be solved in polynomial time is that Sudoku is something that we called an NP-complete problem. And we think that these problems don't have efficient algorithm because we have never found one. And actually, if you find a case where you can actually, of an NP-complete problem that you can solve efficiently, you can get about $1 million or something like that. So if you manage to prove that, that's it, you're a millionaire. Okay, so what are complete problems? So these are problems that are in the class, and every other problem in the class can be transformed into this problem. So in some sense, these are the most general and hardest problems in the class. And if you could solve one of these problems, because every problem transforms into this problem, you could essentially solve every other problem in the class. That's why it's so important. And now, other two examples are the traveling salesman problem of NP-complete problems is the traveling salesman problem, and a mystery one that I will explain right now. So the traveling salesman problem is similar to the shortest path problem. So we want a path that passes through all the cities at most once and returns to Mexico City in under X hours. So it is slightly different now because now we have to go through all of these vertices, but also be back in Mexico City without stepping in a city more than once. And this problem is NP-complete. And this is actually very tragic because this problem is very crucial for delivery companies like Amazon, UPS, or whatever you want, because every day they have to solve this problem, right? So their delivery drivers have to go to some houses and make it back to headquarters in some amount of time, right? And time here is money. So the more they spend on the road, the more gasoline they spend, that costs ultimately millions or billions to these companies. But it is a problem that we think we cannot solve with a classical computer. So that's very tragic. And the other problem is the mystery problem that I told you about before. So let's look at it. So you're given a graph like this, and you're asked to fill in the graph such that there is always a green and a blue circle if connected by an edge. So we want a blue here and a green here, and so on for all of these squares that we see here. And there is a penalty. So for every line where there is no green and blue, then we enforce we say that you get a 5-point penalty. So the answer we seek so the question we seek to answer is, what is the minimum penalty? So in this particular instance, it is not so hard to see that the answer is kind of like this checkerboard pattern, or like the chess pattern. So blue, green, blue, and so on. And this actually gives you a penalty of 0 points. So you can fill this with no penalty. But now let's look at a different example. So now let's look at this triangle. So in the first step, I would do blue and green. But now there is no way that I can fill this one such that it doesn't violate one of these edges. So, and let's just say that we choose blue. So now I have two blues connected by a line, but this one is fine and this one is fine. So the minimum penalty here is 5 points. And now what happens if I give you a much more complicated graph? So it turns out that this problem, it gets a lot harder with the different instances that you might consider, and calculating this penalty is very, very difficult. That's why this problem is NP-complete. So now the examples that I've given you are more on the computer science related. But actually, this is a physics problem, because it is a model of magnetism in materials. So here we have, in physics, we have this thing called the Hamiltonian, which essentially describes the internal energy of your system. And we can think about this as this like constraint that it enforces 5 points, the penalty of 5 points. You see, because in nature, what the system wants to do is to minimize this energy. So let's see. So we want this to be as small as possible. So meaning that I want this as I and as j. So I and j are positions in these graph. And the summation, this just means that I want to sum over all of these lines. And each as I and as j can take +1 or -1, corresponding to the blue and green that I mentioned before. Okay, so to minimize this, I want the product of these is -1, right? For all of those. So yeah, essentially, that means is that I won't enforce, that I won't have any penalty, because I'm minimizing the energy. But when I can't do this, and these are both positive, then I will receive a +5 penalty because of this 5 over here. Right. So the actual problem that we're solving, this is called the Ising spin glass ground state energy problem, which is like, given a Hamiltonian, where now we have this term Jij, which you can think about as the weights on the edges of the graph. So now this is a more complicated problem. You're asked to find what is the minimum energy. That is the NP-complete problem. Okay, so how can I tell whether a problem may be in P or NP-complete? You know, and like I mentioned before, the shortest path problem is kind of related to this traveling salesman problem. Like you have the same, they have kind of like the same essence, or they're trying to ask a similar question, but one of them is easy and the other one is very, very hard. So how can I tell this? So the problems in P are the ones that you can think about as a puzzle, that when you find you're trying different pieces, but once you find a piece that it actually makes sense, then that piece can stay there forever. So little by little, you can make progress towards solving that problem, which is kind of what we saw in the sorting problem. And also, if you take a look at Dijkstra's algorithm, that one is the same. Now, for NP-complete problems, this is a slightly different puzzle that we're trying to solve. And this is called Pantominos, I think, where the goal is to fit all of these pieces into a little like rectangular grid. And the interesting thing that happens here is that you don't know whether you're doing the correct thing at any point in time. And you will only know once you are kind of approaching to the end. So it depends on what you start from the very beginning. And that is a much more complicated problem than this one. Hopefully that gives you some intuition. Okay, but now let's answer the question that we really want here, which is which problems can and can't a quantum computer solve efficiently? So these ones are described by the class BQP, the ones that we can solve efficiently on a fault-tolerant quantum computer. And this is kind of important because right now, current quantum computers don't have enough qubits to solve these algorithms. So we will assume that we have a fault-tolerant quantum computer. So P is in BQP. Why? Because maybe you've seen this before, but qubits are generalizations of bits, and quantum circuits are generalizations of classical circuits, meaning that everything that you can do classically, you can do in a quantum computer. But in practice, this is a different thing. I remember when I was doing one of these like penny lane challenges, and I had to sum two numbers using a quantum computer. And, classically, that is very, very simple. But in the quantum computer, it took me like 2 hours to figure out how to do it. But in theory, yes, quantum computers should be able to solve any problem that classical computers can do. Okay, and like I mentioned, a problem there is Shor's algorithm, the integer factorization, and Shor proved this in 1994. Now, you may be familiar with other types of problems, like Grover, Deutsch-Josa, and Simon's algorithms that you may have already known or you will learn in this hackathon. But those algorithms do not exactly fall in these classes because they already assume that you have this oracle or black box. So it is slightly different. Okay, another problem that is in this class is Hamiltonian simulation. So given a Hamiltonian, like I already explained what these are, but essentially just describe the state of your system, the energy of your system, and an initial quantum state, you're asked what is the state of the system at some later time t. And the solution to this problem is given by the Schrodinger equation. That you can see here, and eventually you get this relationship. And quantum computers are very good at doing this, essentially because they work based on quantum mechanics. And this is very, very difficult for classical computers, which is what I mentioned here. So why is BQP not in P? And this is that generally an n-qubit state can be defined in this way. And there is 2 to the n amplitudes that you need to keep track of, which is a lot of space, memory that you need to keep these amplitudes in memory. But also to manipulate them, you need to do matrix multiplication of exponentially large matrices, which we think that we cannot do classically. And also because there is no superposition, entanglement, and interference in the classical world. Now, the important bit here is that we don't know if NP is in BQP. So essentially what this is saying is that all NP-complete problems that I mentioned before, they seem to be out of reach of quantum computers, sadly. And if it's like that, and now we have another complexity class that is outside of BQP, and this is QMA. So these are problems where given a solution, your quantum state, which here is a quantum state, the answer can be verified with a quantum computer. So, and it has the same relationship that P has with NP. So now we have BQP is included in QMA as well. And I'm running a little bit short on time. So I'm going to skip these examples, which are not too important, and they are a little bit more quantum than it'd be. Um, so I will skip over these. Okay, so the summary is that we have that P is the types of problems that can be solved in a classical computer, and BQP those in a fault-tolerant quantum computer. And what we've shown so far is that BQP is greater or equal than P. We have the same thing for the verification classes. So essentially, yes, we think that quantum computers are better than classical computers, but like I mentioned before, we cannot prove it. Okay, so now finally, which problems can't a classical computer solve? And those ones are, I didn't mention this, but these ones are the exp complete problems and beyond. Like if you remember at the beginning of the talk, I was mentioning about some problems that we know that are not in P. Well, it refers to these. And we also think those that are complete for classes outside P. So here we have, so in this talk, I talked about NP, BQP, and QMA complete. And now, which problems can't a quantum computer solve? Again, those that are exp complete, but also we think those that are complete for classes outside BQP. And here I mentioned NP and QMA complete. And why do we think that we cannot solve this? And this is because if they could be solved, then the implications would go against our intuition and observations, which it's not, how do I say this? It is not an excuse to think that these problems cannot be solved. So it might happen that they could be solved efficiently, right? But we have a strong feeling, and we've done science to think that this is not the case, but we cannot show that. Now I have a bunch of slides, but I unfortunately don't have time to go through them. So yes, I think I will conclude there because we're running out of time. Sorry. Thank you. Let me know if you have any questions, please.
Thank you, Ricardo, for the beautiful presentation. So now
Thank you.
we going for the questions for the public. Just give me a minute.
Mhm.
Okay. The first one is in your research on Hamiltonian complexity, how do you see this field helping us to map the true limits on quantum computation?
I'm sorry, I couldn't hear you very well. Could you repeat the question?
Yeah, sure. In your research on Hamiltonian complexity, how do you see this field helping to us the true limits on quantum computation?
You mean like
Yeah.
what is the what Hamiltonian complexity theory can do to answer this question?
Yeah, let me repeat again. In your
Okay,
research on
sorry.
Hamiltonian complexity, how do you see this field helping to us map the true limits on quantum computation?
Aha, okay, I see.
Yeah.
Yeah, okay. Um, okay, so essentially, Hamiltonian complexity is, I have it here. So this one is only related to problems that have to do with quantum physics. And I think to me, as a physicist, this is a very, very important question because we also want to figure out which problems are hard within physics that are hard for quantum or classical computers, right? And I think by understanding these problems, we can also understand the limits of quantum computers, or are also what they are good at as well. Hopefully that answers your question.
Yes, you did. For the second question, on the flip side, what are the most promising problems where quantum computing can clearly outperform classic ones in the next decade?
Great. Great, great, great. I'm happy you are asking this question because I had a slide here for that. So this slide was exactly about whether current quantum computers, what can they solve or approximate that classical computers can't? And the answer is that we don't know just yet. We don't have evidence of a problem that we can solve with a classical computer or approximate that we cannot solve classically. But we have two candidates. And one of them was Hamiltonian simulation, which I mentioned before. And it is believed that Hamiltonian simulation might be the best of these because quantum computers are effectively, like I said, based on quantum mechanics. So they should be able to do this problem quite easily. So that would be one. And this is an important one because there's a lot of quantum physics that is very, very cool, like superconductivity or superfluidity, that we have currently using in the real world, like in the bullet trains in Japan or China, that use this phenomenon of superconductivity, but we don't understand it enough and we cannot do tests. So we don't understand it. But once we build a quantum computer that can, which I think should be reasonably soon, we might be able to probe into into that physics, which would be very, very exciting. Another one here is on optimization problems. So the one that I mentioned, the traveling salesman problem, is also a very important one. And it is believed that quantum computers can provide speedups for several types of optimization problems using algorithms like the VQE or QAOA that you might have also seen in these like IBM, Penny Lane notebooks as well. So soon we will have probably one of those problems that we can solve with the quantum computer, even though it might not be fault tolerant. Yeah.
Wonderful. We had another question. Hey, you could design a quantum education program for Latin America. What key subjects would you include?
Sorry, could you repeat the question?
Yeah, sure. If you could design a quantum education program for Latin America, what key subjects would you include?
I see. Okay. I would say that a heavy emphasis in linear algebra is essential. I found myself struggling with linear algebra because I didn't think I have enough education of it in maybe even since high school. My undergrad didn't focus too much, or maybe I didn't understand it enough. So I think that if you want to do quantum computing or quantum mechanics, you should really put a lot of emphasis in understanding elementary linear algebra and maybe follow that line of subject to more complicated problems of that type, but everything related to linear algebra. Yes.
We had
Also,
another
coding
question
has
for the
been
yeah.
sorry, but coding has been great as well. So also focus on that. It's very useful, and that is how I got the internships as well that I mentioned before. Thank you.
Okay, perfect. So we had another question for the public. Thank you very much, Ricardo, for your wonderful presentation. You mentioned about the internship. What qualification one must to have to be accepted for an internship position?
Right. Um, it depends. I've heard that, for example, there is internships for. I know for sure that IBM is offering for undergraduate students, and some of these like bigger companies have internship programs for early students or like students that are early in their quantum journey. So, for example, for undergrad as well. So definitely check those out. For the ones that I have been, it was more advanced. Yeah. So I think if you want to really do something uh, breaking science, then you have to have at least a master's, but it is not a necessity. And the other thing that I would recommend is to really attend a lot of these events. That's how I got my first internship. Like the deadline had already closed, but I went to one of these events and I talked to people. And one of them was like, "Oh, hey, send me your CV. We're closed, but I'll try to see if they can consider you." So a lot of networking is also very, very good for these things. Yeah.
Thank you so much. We pass to the other questions. What mission could you share with young Latin American students dreaming on contribute to quantum computing, even for a small institution?
Sorry, could you repeat the first part?
Yeah. What missions would you like to share with young Latin American students dreaming on contribute to quantum computing, even from a small institution?
Mhm. I, if I'm being honest, I don't think that there is such a thing as something stopping you from contributing from being a small institution. There is a lot of knowledge out there, free as well, that you can use to really improve and get better. And I think that pretty much anyone could contribute to something quite important. Yeah, I don't think it's being from a small institution would stop you from anything as well.
Thank you so much. And finally, how can Mexico and Latin American position themselves in theoretical quantum research over the next decade?
Sorry, could you repeat that again?
Yeah, sure. Finally, how can Mexico and Latin American position themselves in theoretical quantum research over the next decade,
I
over the
see.
next 10 years? Yeah.
Okay. Um, that is a hard question because I think that there is not so much, and but fortunately we have people here, even in this event, who are really interested in bringing um, this above, like to surface in Latin America. So I don't know about any measures, but I think just organizing these events, learning about new ideas, uh, getting your teachers also interested in these fields, I think that could really like boost it up. That's what I would say, but I don't really have much, many thoughts about how to do this. But it is true, yeah. It is not a very, um, it's not a big subject in Latin America, like this theoretical physics mixed with quantum computing, but I think it could be, and I hope that it is. Yeah, thank
Okay. Thank you so much, Ricardo. For all the
you.
Cubicle team, we acknowledge that we accepted our invitation to be a speaker for today. And we hope to connect with you in future collaboration and also another keynote for your side in future
Yeah,
events.
for sure.
Thank you so
Thank you
much,
very much.
Ricardo.
Okay. Bye.
Thank you.